Okay, now we are going to learn how to solve the heat equation. So we go straight to the example 9.20. So we have the heat equation itself to be solved. So again, we have multiple boundary conditions in order to solve the PDE, the heat equation. Okay. So the first boundary condition is when x is equal to 0, which is when the position is at origin or 0, the temperature is 0. Okay, this is for all time. And the second boundary condition is the temperature gradient is equal to 0 at a particular position, which is x is equal to L, and this is for all time as well. And when time is 0, which is at the beginning, when range of x is from 0 to 1, these are the behavior of the temperature. This is the temperature profile at the beginning of the when time is 0 and at range of x here. Okay, so how to solve the heat equation? We just use the heat equation formula or the solution of heat equation formula right here. So we have multiple unknown, so A and B will be found afterward. Lambda is related to the heat equation, to the formula of the heat, and kappa is the given constant. So we are going to find what we are going to find is lambda and alpha, okay, and as well A and B. All right. Okay, now we consider the first first boundary condition. So the first boundary condition, when x is equal to 0, the temperature is equal to 0. Okay, so when we put x equal to 0, so this is equal to 0, this is equal to 0. So what will happen is this one is equal to 1, and this one, because sine 0 is equal to 0, cos 0 is equal to 1. So we have eliminated this component, but we are unable to eliminate this one because this is 1. Okay, therefore B need to be 0. Okay, therefore this from this boundary equation, we know that B is equal to 0. Okay, therefore we can get that T is equal to 0. Alright, hopefully you understand that, how I get that B is equal to 0. So now we know that B is equal to 0, so we substitute this one back to this, and then we can get this equation. Okay, so now we have used the first boundary condition. Now we consider the second boundary condition, which is we need to find delta or dt dx, okay, the temperature gradient. So we need to differentiate this one with respect to x. So when we differentiate that, first of all we need to know the second boundary condition. When x is equal to L, the temperature gradient is equal to 0. So first we differentiate it and we get this one. Okay, and then we substitute with x with L, so this one is equal to L. Okay, all right. So since this all need to be 0, we cannot eliminate, we cannot have alpha equal to 0 or etc. So what we can do is we can make this one is equal to 0. Okay, the cost component equal to 0. How to do that? Now we want to make the cost lambda L equal to 0. So we know that how to make a cost equal to 0 is by cos 180 degree. No, cos 90 degree. Sorry, cos 90 degree. So pi over 2. And what is n? N is 0, 1, 2, 3. So n is integer. Alright. So we know how to make cos equal to 0. So these are the formula that we need to have. Okay. And we can put L to the right hand side. And this is the formula that we need to remember. So this is the formula for lambda. Remember that we need to find lambda. So this is the formula that we have. So we put this back to this equation. Okay. So okay, right. So we just replace the lambda. Okay. Okay, so no. I think I made a mistake. Actually, we put this formula back to above right here. Before we do the differentiation. So that's why we don't have a small lambda right here. Okay. So when we put back the lambda inside here, so we can have the updated solution. Okay, and that's why we have this solution. Okay, so this is the lambda, and we have x right here. Okay, so that is the updated. So this is the current solution that we have. Now we want to consider the third boundary condition, where if we go back, when time is 0 at the initial condition, and range of x is 0 to 1, we have this equation. Okay, that is the behavior of temperature. So we just put them inside this equation. So we have time t is equal to 0. So we put that inside the equation. So we have time right there. So we can eliminate the exponential component. Okay, because they is equal to 1. And now we consider the boundary condition at the initial condition. This is equal to the given function, and then we compare both of them, and we can see that when we compare, first of all, the T naught and A, we can know that A is equal to T naught. Okay, and then we consider this component and this component. We know that n is equal to 1. Okay, we can find that n is equal to 1. Okay, and then before we finish, before we substitute back to the updated solution right here, we need to replace alpha. So we know the kappa, we know the lambda already, so we can rearrange that alpha is equal to this function, and then we replace lambda with the given function, with the obtained function, which is this one. So we replace substitute lambda, so we get the alpha. Okay. So now I want to clear back everything. So now we consider this equation. Okay, we know lambda already. We know what is A. We know what is this, the updated this. Okay, so we just substitute. So alpha is this one. Okay, when you put lambda right here, you will get that alpha is this one. Okay, and then we substitute A with TO, and we substitute N with 1, so we get this one. Okay, so that is the solution for example 9.20. Thank you for listening.